today it's working. I sure thought it did the other day, but we didn't get a video, so not sure what happened. Okay, so I have talked to you about the ion sheet. I asked a student and they reminded me that yes, I have gone over the ion sheet. Is that correct? Have I told you on the ion sheet? Okay. All right, so I'm not going to go over that again with you. Have we also labeled our periodic table? Okay, that's what I thought. So we are ready then to go straight into Dalton's model of the atom. We'll give you a big picture for today. I don't do history. I do not teach history in this class. I know if you had a high school chemistry class, a lot of times the teachers spend a lot of time on history of the atom. I don't spend much time on the history of the atom. Basically, I'm going to go back and say, we know that through scientific discoveries that we have protons, neutrons, and electrons. Those are the subatomic particles of the atoms. They were determined by lots of experimentation by a lot of people in the 1800s, some in the 1700s, but mainly in the 1800s. Now we know we have these things. One person I am going to mention just a little bit about his model of the atom is Dalton, because mainly his model of the atom is the basis of where we get our modern atomic theory today. And so that's why I even put these postulates on your paper. So Dalton's model of the atom, approximately around 1810, what I want us to do with this is simply look through these and say, do we agree with this now or disagree? And then what came of this? What did we get from this information? So you've got the 6 postulates here. So we're going to take these step by step and say, do we agree or disagree? So number 1, elements are composed of minute, indivisible particles called atoms. Do we agree or disagree? Indivisible, minute particles called atoms. Agree or disagree?
Well, not with the indivisible.
Correct. So we have to say we disagree. Overall, it sounds pretty good, but we have to disagree because we know that they can be divided. So we have to disagree because we know they can be divided. All right? Atoms of the same element are alike in mass and size. And actually, I see a correction in my notes. I have here in my notes that this was actually 1804, not 1810. Not that that matters to you, but 220 years ago. Pretty impressive, honestly. Isn't that pretty amazing? All right, so atoms of the same element are alike in mass and size. What do we think? Agree or disagree? Atoms of the same element. Who's had a chemistry class before? Atoms of the same element are alike in mass and size. Agree or disagree? Anybody disagree? Nobody disagrees? We have to disagree. I was hoping somebody knew that. Anybody know why? It's a funny word. Isotopes. Isotopes. We have to disagree because of isotopes. And we're going to define isotopes. I'm going to real quickly tell you what they are. Isotopes are atoms of the same element that have different mass and different size. Different mass, not size, but mass. So again, he's really, really close. Atoms of different elements have different masses and sizes. Now you're scared to agree with anything. Atoms of different elements, so carbon and nitrogen and oxygen, are different mass, different size. Agree or disagree? We agree. That is true. We agree. We agree. However, so I'm going to put we agree, however, nuclear isotopes may have same mass. So part of it is correct, part of it is not correct. Part of it is correct and part of it is not correct. So in other words, we agree with the fact that they will be different in size, and that's called atomic radius, which we're going to deal with next week. but we don't agree on mass. And I'll tell you what I'm talking about here. If we look at oxygen, for instance, on the periodic table, oxygen, the mass, the average mass of oxygen is 16 AMU. And then you say, okay, well, let's look at fluorine. Fluorine's average mass is 19 AMU. Well, what actually can happen is fluorine can look like oxygen by mass. Oxygen can have an isotope that will look like fluorine by mass. So we do have some problems with this. Nuclear chemistry is where this comes into play, as well as this one, because you can split an atom, and this is what we were talking about earlier, and again, it's nuclear chemistry, which of course would not have been thought of at all in Dalton's time in the 1800s. But I agree with you, definitely, you know, we might even put dis/agree. It's that one's a really tricky one. All right, number 4, chemical compounds are formed by the union of 2 or more atoms of different elements. Chemical compounds are formed by the union of 2 or more atoms of different elements. I've pretty much written that before. Agree. Haven't I written that whenever we had compounds? Didn't I write what were compounds? Chemically combined atoms? Yeah, and that's what we do agree. Atoms combine to form compounds in simple numerical ratios such as 1 to 1, 2 to 3, etc. Now, to understand what that is even saying, think about you're doing nomenclature in lab right now. Think about in lab when you write formulas. Do you have any formulas that have decimals? Are you doing anything like Na 2.5, O 7.6? No. What is everything? 1 to 1, 2 to 5, 3 to 2, 2 to 3, 2 to 1, something like that? Are they all simple numeric ratios? Yes, so we agree. We agree. Atoms of 2 elements may combine in different ratios to form more than one compound. Let me give you an example of potentially of what that means. Atoms of 2 elements, 2 different elements, may combine in different ratios to form more than one compound. So that means, let's just take sulfur and oxygen. Just those 2 elements, can sulfur and oxygen combine in different ways to make 2 different compounds or more? Yes, yes, they can. Carbon and oxygen do. What's an example for carbon and oxygen? Say it again, Lucas. CO2. And CO. CO and CO2. Does that make sense? So if we have carbon dioxide and carbon monoxide, are those 2 compounds of carbon and oxygen that are different? Yeah, so we agree. We agree. I am impressed with Dalton, by far, very, very much impressed. I mean, you've got to realize this is before. So Kentucky, we started coming into Kentucky in the late 1700s. Follow me? Bowling Green, I think, was organized, I think it was 1790 something. I can't remember exactly when it was. So this is just a little bit after that. Had we even, I mean, are we talking Little House on the Prairie traveling west scenario yet? No. We're just now crossing, this is the time period where we're just now crossing through the Cumberland Gap. Okay, that's where this is. We have just crossed into the Cumberland Gap in the United States. This all occurred in England and Britain. This all occurred there. It didn't occur here. So pretty good, in my opinion. Pretty good, I think. In fact, it's so good that we have 2 laws. 2 laws that came about as a result of this. 2 laws. We have the law of definite composition and the law of multiple proportions. Which of these do you think the law of definite composition comes from? You don't even know the law yet, but you should kind of be able to tell me. Which of those 2 postulates do you think helped form the law of definite composition? Has to be something we agree with, obviously. Law of definite chemical composition. Help you out. Which one? 4, definitely 4, and 5. 4 and 5 is where that comes from. And here's the law. It says a compound always contains 2 or more elements chemically combined in a definite proportion by mass. A compound always contains 2 or more elements chemically combined in a definite proportion by mass. Ryan, wake up. Ryan, wake up, buddy. All right, a compound always contains 2 or more elements chemically combined in a definite proportion by mass. That's the law of definite composition. So I'm going to give you an example of this. Water is always 88.8% oxygen and 11.2% hydrogen. I'm telling you this information. Water is always 88.8% oxygen and 11.2% hydrogen. Which of these is water? Which of these is water? A, which is 44.4 grams O and 5.6 H. B, which is 66.6 grams O and 8.4 grams H. Or C, which is 59.2 grams O and 8.4 grams of H. Which of those is water? If you need a calculator, grab a calculator. Hopefully some of you can do this in your head, but if you can't, then grab a calculator. In fact, you better grab a calculator. Grab a calculator, okay? Grab a calculator so I can tell you how to do one you can't do in your head. This one you can do this in your head. But grab a calculator so you can do one that you can't do in your head. All right, how do you know it's A?
Because 44.4 plus 5.6 is 50. So if you I guess you could say if you divide 44 from 50, it'll give you 0.888. Or you could just think 44.4 times 2 gives you 88.8.
What he's doing is the math in his head. Is it, I made A super easy. Is A exactly half of what I told you originally? But that's what I'm saying. For those of you that are not math, you can't see that immediately. Then what is a proportion? It's a ratio. So set up a ratio. Take 88.8 divided by 11.2. Take 88.8 divided by 11.2 on your calculator. What is that ratio? 8.4. That's the ratio that you get. It's an 8.4 to 1. Now take 44.4 divided by 5.6. See if it equals 8.4. Then take the next one. See if it equals 8.4. Take the next one. See if it equals 8.4. And then tell me which of these, could be more than one. Yes?
Okay, what are we doing wrong? Because whenever we divided that, we got 7.9.
I don't have a calculator. I don't know. Do 88.8 divided by 11.2.
Yeah, it's 7.9.
7.9? Okay. So 7.9. I'm not doing it. I'm just listening. So 7.9. Thank you. Everybody get 7.9? Okay. So now see which one of these are 7.9. So run through all of those and see which ones of these are 7.9. So we know this one is. So this one definitely is. All right, what else is? B, okay. What's the ratio for C? So it's not, is it? Does that make sense? So that's what you'll do. You'll set up a ratio, understanding how to set up a ratio, because that's what it tells us, and that's literally what number 5 had said. They're going to combine in simple numerical ratios. And so these will always have the same ratio. So if you get a compound that has the same ratio as water, you have water. No other compound has that ratio. Now, let me go a step further. In real life, we as chemists, industrial chemistry, research chemists, have methods and chromatograms, gas chromatography, which is something we did, thin layer chromatography, gas chromatography, which is similar except it's gases going through a tube that contains a stationary phase. Gas chromatography, along with other different instruments, can literally give us percentages of elements in compounds. So if we have an unknown compound, what would be tests that you might do before you ever use your gas chromatograph or other things? What would be tests that you might do in order to determine that you have something? What would you do first, based on what you've already learned in lab? What could you do? What's the first thing you could potentially do? You have an unknown substance. Say it. Well, it depends on does it have chunks in it. If it had chunks in it, you could filter it. Let's say it's a homogeneous solution. Let's say it's a solid. Let's just say it's a solid. What would you do? See if it is what? Soluble in water. Could you see if it's soluble in water? Is that something you could do? You would take part of the sample and see if it's soluble in water. Could you also test its solubility in other things? Potentially, yes. And that would help you narrow it down. Then, literally what we can do is we have instruments that we can put a sample of the substance in and see what percentages of elements are in it. Based upon those percentages, we can find the formula. That's how we can do it. We're going to learn how to do that later in this class. But how can we do it? Why does that work? Because every compound has a set composition. Every compound has a set composition. That is who that compound is, a set composition. It never changes because it's a compound, okay? The law of multiple proportions says that atoms of 2 or more elements may combine in different ratios to form more than one compound. Atoms of 2 or more elements may combine in different ratios to form more than one compound. Which postulate does that apply to? Say it. 6. It's almost word for word, isn't it? What he said in 6? It's almost word for word, and that is what we've already talked about. So some examples of those would be CO and CO2. Another example would be water and hydrogen peroxide. Another example, here's one that is different than a simple example, but it is another example. HC2H3O2 is vinegar, and C12H22O11 is sucrose, which you and I call sugar. Are those very different? Vinegar and sugar are quite different, but what do they both have? Carbon, hydrogen, and oxygen. In fact, you're going to find tons and tons and tons. When you all go to 107, those of you that have to take 107 and 108, you're going to find in 107 that there are so many carbon-containing compounds that that definitely supports the law of multiple proportions, because there are tons and tons and tons. You and I are carbon-containing compounds. Every living matter, everything that's alive is a carbon-containing compound. So I am impressed with Dalton. I think it's important to understand these two laws. Read over these postulates every so often. I will not ask you those word for word, but obviously you should recognize whether something was one of his postulates or not. So if you read over these every day, I think you're going to remember them pretty well. Know the two laws, though. You definitely need to know the two laws. All right, so after Dalton did his work, and very soon after, we really started looking, the scientists, I shouldn't say we, started looking at atoms, and we determined, and this is all the stuff that I don't go into the history, we have the 3 subatomic particles, protons, neutrons, and electrons. In my experience teaching, this is where I find that teachers, for some reason, spend time with you all on, and I don't understand it myself, because this is like the most complicated, in a sense, part of chemistry that's useless for so many people who don't understand the real picture of chemistry. But most of the time, a lot of you have learned these. How many of you have never heard of these? Never? That's what I thought. All of you have heard of these before, but you don't, but you don't understand separating a mixture like we did, which is really more chemistry fun than this is, for sure. All right, symbol for protons is P. Neutrons is N, electrons is E negative. Sometimes we'll use a positive for protons as well, which indicates the charge. The charge is +1 for protons. Neutrons are neutral, and electrons are -1. The relative mass and the unit AMU is atomic mass unit. The relative mass is 1 AMU for a proton, 1 AMU for a neutron, and it's actually 1/1837 AMU for an electron, but we say, don't worry. Just don't count it. Don't worry about the mass of an electron. It's so small, we don't worry about it. It's definitely not a participant in the mass game. So just don't worry about it. It's negligible is the word we use. Negligible. Not enough there to worry about. All right, couple notes on protons. Protons are the same as atomic number. That is a huge, huge concept. Positive, same as atomic number. So protons are same as atomic number. They give the positive charge to the atom. They also give mass, and they are found in nucleus. So I had too much to write in that little box, so I'm putting it up top there. So they're the same as the atomic number. They are found in the nucleus, and they give mass. Who else gives mass? Look right there. Who gives mass? Not electrons. Neutrons. Neutrons. Don't worry about the mass of an electron. It does not give mass, okay? So neutrons give mass. They give mass. They are found in the nucleus. And protons plus neutrons equal atomic mass. That is a pretty important concept there. Protons plus neutrons equals mass. Electrons are the player. Electrons are either lost, gained, or shared to form compounds. They are, honestly, for our purposes for the next week or so, the most important thing we're going to talk about, electrons. Oh, we're going to spend a ton of time talking about electrons. It is electrons that are going to do their doing that gives the colors that you're going to see next week in lab. That's how important they are. That's how cool they are. It's what do electrons do that causes the colors you're going to see with a flame test next week in lab. So electrons, we're going to spend lots of time talking about electrons. Why am I, based on what I've just written, why do we spend a lot of time talking about electrons? What I just write about them. They're the ones who play the part in forming compounds. They're so important. Electrons are so important. All right, so I'm going to basically talk about some of the same things I've just talked about, but rewrite it so that you get it in your head, these different things. So atomic number is symbolized with Z. I will hardly ever use that symbol for atomic number, but I am putting it there because other people do. Atomic number equal protons. Atomic number equal protons. They also equal electrons in a neutral atom. That means a no charge atom. That means a free element. When an element is free, it has no charge. If it's out in nature, it has no charge. The atomic number is the identity of the atom. What would be your atomic number at Western? Your 800 number. Your 800 number or your Social Security number for the IRS is your atomic number. That's what that would be, okay? Same kind of thing. You cannot change the atomic number for an atom. If you do, it's a different atom. You can't change it. All right, atomic mass. We've already said what atomic mass is. It's symbolized with A. What is atomic mass? That's right. Protons plus neutrons equals mass. Protons plus neutrons equals mass. What's in the nucleus of the atom? Say it again. Protons and neutrons are located in the nucleus. Tell me a little bit else about the nucleus. If protons are and neutrons are located there, tell me what else you know about it. What charge does it have? Positive. Why? Who's there? Protons are there. So it's positive charge. Positive charge. What else is there? All of the mass. Contains all the mass. Also, which is not written here, but you do need to know, not need to know, it's interesting to know, the nucleus is very tiny. It's very tiny and dense. Very, very tiny and dense. The relationship of the nucleus in the atom has often been described as a P in the middle of the 50-yard line of a football field. Think of a green pea. A green pea. Mama said eat your peas. A green pea in the middle of the 50-yard line of a football field. And that P is the nucleus, and all the grass is the electron cloud. Pretty dense, right? That's the core, that's kind of the relationship, the illustration they give. Neutrons, so I've told you what the mass is. You know how to find protons. How would you find neutrons? Say it again. Mass minus protons equals neutrons. mass minus protons equal neutrons. And I always want you to have that as a whole number. Neutrons should always be a whole number. Now, before we talk about ions, I need to make a comment about my class and the periodic table. Okay, so I'm going to block this statement off so that we all are on the same page. In Mrs. Brooks' class, round atomic mass from periodic table to nearest hundredth. That's my class. In my class, other classes may tell you to do something different. I'm telling you, round atomic mass, when you get it from the periodic table to the nearest hundredth. By doing that, we are all on the same page. Okay? That way we all get the exact same number, rounding properly. So let's just stop real quickly. Grab your periodic table because you're going to need it for the next page. Grab your periodic table. All right, grab your periodic table. Tell me, what is the mass of sulfur?
32.066.
How did I just say to round it? 32.07. What's the unit? AMU. Okay. What is the mass of potassium? 39.10 AMU. Okay? That's what we're going to be doing. You're going to be doing more of this on the next page. That's why you needed it. All right, so let's talk about ions, and we're going to do some practice. So ions are charged atoms due to the loss or gain of electrons. Okay, let's talk about that real quick. Who cannot change in an atom? Who can't? You're right. Who cannot change? Who cannot change? Say it. Somebody say it. Protons. Protons cannot change. Why not? Their identity. The protons are the identity. Protons cannot change. I already said electrons do what? Lost, gained, or shared, yes? And neutrons definitely we're going to see can change, but what is the only thing that makes a charge? Positive and negative, right? Positive and negative make charges. Who's positive in the atom? Protons. Who's negative? Negative, not neutrons. Neutrons are neutral. Who's negative? Electrons. So, again, let me get everybody awake here. What are the two things that make the charge in the atom? Protons and electrons. Who cannot change? Protons, because that's who the atom is. That's the atomic number. Which means, who's the only thing left to change that makes the charge? Electrons. Electrons are the only things that are going to play a part in forming ions. Ions. That's all that's the only thing that can make it. And look, it says charged atoms due to loss or gain of electrons, because protons do not change and neutrons don't have anything to do with the charge anyway, so that doesn't matter. Now, keeping that in mind, let's figure this out. Cations, I'm going to tell you, are positive due to, and we're going to fill that in a minute, anions are negative due to now, you've all been exposed to the words cations and anions. From where? Well, besides high school. Here. Where? Here. Our class, but where else? For 3 or 4 weeks now. Lab. What kind of compounds make up anions and cations? Ionic compounds. Okay, so you've heard this a lot already, but you might not have known how they're formed. So now we're going to get into that part. So the cations are positive due to, now think. What are the only things that can change that affect the charge? Electrons. So how do you become positive? Say it. Lose electrons. Positive due to loss of electrons. Positive due to loss of electrons. Because electrons are negative. Anions are negative due to what? Gain. Anions are negative due to gain of electrons. The easiest way to remember this is in real life. If you surround yourself with negative people, what do you become? Negative. If you're doing that right now in your life, get rid of the negative people in your life, the negative influences in your life, and what are you going to become? You lose the negatives, what do you become? Positive. Say that again. You lose the negatives, you become positive. If you gain negatives, you become negative. Caleb, put that phone up. What is the deal, man? It's 10:28. I'll tell you the time. It's right here too, isn't it? Okay, just ask me, what time is it, Miss Brooke? That way you don't have to pull that phone out, okay? All right. Now, flip the page, and we're going to do this exact same thing that we've been talking about for each of these particles. This is why you needed your periodic table. So grab that periodic table, and we're going to dissect the following particles. So find sodium on your periodic table. Tell me how many protons sodium has. Say it. Come on, find it. Here, some of you are not even knowing where to look. Guys, look at your periodic table. Look at the top part of your periodic table. Do you see where it says element symbol H right in the middle of the periodic table? On the far top left, what is that? The atomic number. What's that the same as? Atomic number is always the same as what? Protons, and it is equal to electrons if the atom is neutral. Is this a neutral atom? Is there a charge? No, there's no charge, so it's neutral. So how many protons for sodium? Come on, everybody. 11. What else is 11? Electrons. What else is 11? Atomic number. Why? Because protons equal electrons, and protons are the atomic number. When it is neutral, the protons equal the electrons. How do we get atomic mass? Look at the periodic table. And round it how? What is it? Go ahead. What's the atomic mass? Round it like I've told you to round it. 22.99. What's the unit? AMU. Are you all finding this on your periodic table? Okay. All right. How do we get neutrons? Mass, take away the protons. So, and round it to the whole number. So we're just going to put 23 minus 11 equals, what is it? 12. Now you do 10. Right now you do 10. All right, what do you find for the protons for 10? 50. What else is 50? What else? All right, what is the mass? 118.71 AMU. And then how do we get neutrons? 119 minus 50 equals what? 69. Yes or no? Everybody with me? Okay. Now we have 3 ions. So these 3 ions we are looking at and we are saying, okay, what did they do? What happened to give them this charge? So let's deal with the positive 2. What happened to give it a positive 2 charge? It lost what? That's right. So lost 2 electrons. Let's go ahead and do the next one. What happened to make this phosphide with a negative 3 charge? It gained what? How many? 3 electrons. It gained 3 electrons. What about barium 2 plus? What happened? It lost 2 electrons. It lost 2 electrons. So now I'll do Fe2 plus with you, and then I'm going to let you do the other 2. What do you know about protons for Fe? No, protons. 26. Protons don't ever change. So that means automatically what else is for sure 26? Atomic number. But electrons have changed. That's what gives us the positive 2 charge. So how many electrons do we have? 24. Very good. Very good. Mass is no different. What's the mass? Good. 55.85 AMU. And how do we determine neutrons? 56 minus what? 26 equals 30. Yes or no, guys? All right, you do the next 2. You do the next 2. All right, what do you know about phosphide protons? 15. What else is 15? Atomic number. It's phosphide with a negative 3 charge, so how many electrons does it have? 18. Very good. What's the atomic mass? Good. AMU. Very good. That means the neutrons, we do 31 minus 15. So what do you get? 16. Very good. Question on that one? All right. Barium 2 plus. What's protons? Who else is 56? Atomic number. Good. Electrons, it's barium plus 2. 54. Very good. What's the mass? Good. AMU. And 137 minus 56 equals what? 81. Good job. Is this making sense? You're going to have to do stuff like this on your homework. Okay? I'll open up the homework this morning also. It's not open yet, I don't think. I might have done that. I may have already done it, but I'll look and see, make sure. Okay? All right, let's talk about isotopes now. So isotopes in the Dalton's theory back here, I put atoms of the same element are alike in mass and size, and then I said we disagree because of isotopes. So what is an isotope? An isotope is, or are, atoms of the same element that have different mass due to say it.
Because of the neutrons.
Different number of neutrons. That's exactly right. Atoms of the same element that have different mass due to different number of neutrons. That's exactly right. Think about this for just a minute. I'm telling you, atoms of the same element can have different mass. You should know, though, what's the only thing that could be different if it's the same element? What are the two things that make up the mass of an atom? Protons and neutrons. Who can't change if you are that atom? Protons. So it's the only thing left that could change. Neutrons. Neutrons. I have this vision, which is just stupid, but it's just how I think. I think of neutrons as fat. That's kind of how I think of neutrons. They just add mass. They're just there. They just provide mass. Now they do other things, but they're not fat in the atom really. That's how I equate them. They just provide mass. That's what they do. They have no charge. They don't affect compounds. They just provide mass. That's what neutrons do. The periodic table mass that you and I see is actually an average mass. It is an average mass of all isotopes of that atom. And it's an average, can't spell average, based on abundance. It's an average that's based on abundance. So it's an average mass based on the abundance of that particular isotope. We'll give you an example of what I'm talking about here. Copper has an isotope that has a mass of 63. So copper 63 is the name of that isotope. It has a mass of 63. That's its mass. I'm going to put a little note there. That's its mass. And we know that there are 69.09% of all atoms are copper 63 atoms. Of all atoms that we know of, all that have been discovered, 69.09% of all copper atoms are copper 63, copper with a mass of 63. We know also that there is an isotope of copper called copper 65. Again, that's its mass. And we know that we have 30.91% of all copper atoms are copper 65. Look at your periodic table. Look at your periodic table. What is the average mass of copper? What do you see on the periodic table? AMU. So, does that make sense? Does it make sense that the average would be closer to 63? Does that make sense? Because do we have more copper 63s? Yeah. So it's an average based upon abundance. When you get protons and neutrons, you will determine the mass by adding protons and neutrons. But if I don't give you protons and neutrons, then how do you get the mass? From the periodic table. And then it's an average mass. And we're going to do some like that. I'm going to talk about what I mean. Before we leave that and start doing those, though, I want to show you 3 special isotopes. Basically, there are not normally names for isotopes. If I called this whole room isotopes of the element people, and our symbol was up here as PP, you guys are beautiful, individually made people, and each of you is your own named isotope. But most of the time, we don't have isotopes that are named like that, but hydrogen does. Hydrogen has 3 isotopes, and they are special in that they have names. And their names are protium, deuterium, and tritium. Protium and deuterium and tritium. Have any of you ever heard of any of these before? Tritium? You've heard of tritium? Good. Have any of you been to the planetarium show where it talks about how a star is born? Anybody been to that? If you've ever been to that or ever had an astronomy class, I think they kind of made you go if you had an astronomy class, then they talk about deuterium. They talk about it because that's how the sun, that's how stars are fused together, and that's where the energy comes from. It talks about deuterium bonding with protium to make helium. I mean, it's a pretty cool scenario what they're talking about in there. But you're going to hear these potentially in some of those situations. And tritium I'm going to talk to you about. Again, most isotopes aren't named. And I'm going to fill this in just a minute, but I'm going to also show you how we normally write isotopes at the same time. Typically, isotopes are written with a name, symbol, and mass. For instance, and I'm not even going to write it down because it's already right here. Do you see copper 63? That's typically what we'll write. But hydrogen's special. It has names, protium, deuterium, and tritium. The names actually came from the mass. So I'm going to show you, this is the mass of protium, 1, deuterium, 2. What do you think tritium is? 3. So how many protons would this have? How many neutrons would this have? Because protons plus neutrons equal mass. They're all hydrogen. Make it easy. So how many protons do they all have? 1. Why? Because they're all who? Hydrogen. Okay? So then we look at protium. How many neutrons does protium have? None. None. You don't have to have neutrons. Because what's 1 plus 1 would be 2, so that would be who? Who has 1 neutron? Deuterium. Who has 2 neutrons? Tritium. Tritium has 2 neutrons. Does that make sense? So again, this is a good visual for what are isotopes. Isotopes are atoms of the same element. They all have the same number of protons, but they have different numbers of what? Neutrons, therefore they have different mass. So if we were naming hydrogen's isotopes without their special names, then we would say protium is hydrogen 1. Do you agree with me? Does that make sense? Other ways you have actually heard of these before, I would bet. So these are all going to be examples here. Have any of you ever heard of carbon-14? Some of you have. That's the mass of that isotope of carbon. Now look at your periodic table and tell me the average mass for carbon. 12.01. So carbon-14 is a radioactive isotope that actually is used to date once living things.
Carbon dating?
Carbon dating, that's exactly right. That's exactly right, carbon dating. I haven't tried it myself, but ha ha ha. You don't get it, do you? Some of you do. Okay, all right, so carbon-14, some of you may have also heard of U-235, uranium-235 or uranium-239. Yes, uranium-238, very good. All of those are different isotopes of uranium. And uranium, some of those isotopes are used in nuclear reactors or nuclear energy and nuclear weapons. So that's all of those. You may have heard of those before. And iodine 131 is used in medicine a lot. It's an isotope used in hyperthyroidism in medicine. So those are all different isotopes. Some of these are radioactive, some of these aren't. So that's one method of naming that, probably the most common. This would be the most common method because this is where you could have heard of things before written or listed this way. The isotope symbol is not one that you've probably seen or heard of before, but we're going to do it because it's a very concise way of doing it, and we're in a chemistry class. So, isotope symbol is when you have the atom symbol with mass as superscript, that means up high, on left, and protons as subscript on the left. And the example shows you the best rather than just writing those words. So if we have symbol of the element, so whatever the symbol of the element is, this is the symbol, I'm just using X as my example. That is the symbol of the element. Whatever the symbol is listed here. Then you have the mass of the isotope. You have the mass of the isotope, and then here you have the atomic number. Now, I wrote this as atomic number. Here I said protons. Why can I do that? Because they are the what? Same. Don't get confused. I'm doing that on purpose to get you to pay attention. Wake up over there. Okay? All right. Now, let's do protium, deuterium, and tritium with their isotope symbol, and then you're going to do it below. So let's do protium, deuterium, and tritium with their isotope symbol, just like that. What's the symbol of each one of them? Say it. H. Why? They're all who? They're all hydrogen. So H, H, H. Okay? Wake up, boys. All right? All right. What's the mass of protium? What's the mass of protium? 1. So what goes up here? 1. How many protons does protium have? Say it. 1. What's the mass of deuterium? 2. So right here, 2. What's the number of protons? 1. What's the mass of tritium? 3. What's the number of protons? 1. Does that make sense? Now, if you all think I'm goofy, let me just tell you a story real quick. Tritium. Tritium is used, it's radioactive isotope that actually gives off light as it decays. A long time ago in another world, I'm not done yet, we're going to do these, but you need to hear this because I need you to know these are real things. I'm not making this up, okay? A long time ago in another world, I had a company, one of our companies was energy saving company, and in that energy saving company, we were actually looking at diversifying into exit signs. Why? Because exit signs are important in a room. If this room were totally dark, would you want to find the exit? Absolutely. So exit signs that we were looking into getting into selling and distributing were tritium-filled exit signs. Because guess what tritium does? It gives off light as it decays. So guess what? Do they require energy? No. They don't require energy. So you put that exit sign in a building that has no electricity, can you find your way out? Yeah. Isn't that wild? So I'm not just making this up. Look it up. Tritium exit signs and you'll find it. Also, it's in scopes. Military uses tritium for several different things, for their glow-in-the-dark stuff. All right, we're going to write isotope symbols here. What is the element with 16 protons? All right, so we know sulfur. What automatically do we put down here as 16? the atomic number, correct? All right, what do we have to put as the mass? It's the mass of this isotope. So we add those together. What's 16 plus 17? 33. Now, there's one more thing you have to do. Can an isotope be an ion? Yes, it can, because they're atoms. They're atoms, they can be. How do you know if it's an ion? I'm showing you guys, I wrote it down. What did I write here? Look, is this one an ion? How do I know it's an ion? It has 18 electrons and it has how many protons? So what's the charge? Come on, -2. -2. Let's do 2 more, guys, because you're going to have to do these for homework. Let's do 2 more. Come over here on the right-hand side. Who is this? Iodine. Which iodine is it? Add protons plus neutrons. Guys, you got a calculator in front of you if you can't do it in your head. What is it? Come on. 125. What do I put down here? 53. What's the charge? -1. All right. You do this one right now, real quick, and then we'll go. You do this one. You do this one, and then I'm going to finish filling these out so that you have the answer key. I'm not coming back to this on Tuesday. Finish filling this out. Who's 92? Uranium. What's the mass of this uranium? 239. What goes down here on the atomic number? Is it an ion? No. All right, I'm going to keep talking it through. If you need to leave, go ahead and leave, but I'm going to keep talking it through. This one is carbon because it has 6 protons. The mass is 6 plus 7, which is 13. 6 protons, and it is not an ion. This one is barium because it's 56. 56 plus 80 is 136. The protons is 56, and it is an ion with a charge of +2. 28 protons is nickel. The mass is 59. It is 28 protons, and it is an ion with a +2 charge. So practice those because we were very, very fast on that. So practice those, do them again. And I'm going to record this for everybody here. There are 20 people absent today. 20 people in this class are missing today. I hope those people will show up to class from now on.